Welcome to ScienceCover.com. This session is on acceleration. The aims of the session are to learn how to calculate acceleration, to rearrange the equation to get values for time, or initial or final speed, and to know how to use the acceleration equation when we see a deceleration. Before we begin, pause the video and attempt the do now task. Let's check the answers. Describe what is happening to the vehicle in each of the following velocity time graphs. A is showing a constant speed. B is showing a stationary object. C is showing an object that decelerates. And D is showing an acceleration. Write a short story to describe the motion shown by the graph. We could write any short story, but it must describe the acceleration over the first 10 seconds, driving at a constant speed over the next 10 seconds, being stationary between 20 and 30 seconds, accelerating between 30 and 40 seconds, and then decelerating between 40 and 50 seconds. Let us begin by looking at how to calculate acceleration. Acceleration is a change in speed. We measure the acceleration in meters per second, or more commonly as meters per second squared. To calculate the acceleration, we need to know the initial speed, which we use the letter u to represent, the final speed, which we let the letter v represent, and the time over which the change in speed has occurred, which we'll use the letter t to represent. So an acceleration can be calculated by taking the change in speed and dividing it by the time over which the change of speed occurs. So this is v minus u divided by t. Let's look at an example of how to use the acceleration equation. A child releases a helium balloon which accelerates upwards from 0 meters per second to 5 meters per second over a 10-second period. Calculate the acceleration of the balloon. So our acceleration equation is that A is equal to v minus u, that's the change of velocity, divided by time. We know from the question that v, the final velocity of the balloon, is 5 meters per second. U, the initial velocity of the balloon, is 0 meters per second, and that the change in speed is happening over a 10-second period. We can now substitute these numbers into the equation. This tells us that A is equal to 5 minus 0 divided by 10. And this gives us 0.5. The units for acceleration are meters per second squared. In this example, our golfer tees off, striking the ball so that it accelerates from 0 meters per second to 30 meters per second over a 2-second time period. Calculate the acceleration of the ball. So again, A is equal to v minus u divided by t. And we know from the question that v, the final velocity of the ball, is 30 meters per second. U, the initial speed of the ball, is 0 meters per second. And t, the time over which the change in speed takes place, is 2 seconds. We can now substitute these values into the equation. So we now have A is equal to 30 minus 0 divided by 2. This gives us 15 meters per second squared. Pause the video now and attempt task 1. Let's check our answers. In number 1, the acceleration equation is a equals v minus u divided by t. In number 2, the units for acceleration are meters per second squared. In number 3, the acceleration of the boy is 2 meters per second squared. In number 4, the acceleration of the car is 2 meters per second squared. In number 5, the acceleration for the T-Rex is 10 meters per second squared. In 6a, the acceleration of the Porsche is 4.22 meters per second squared. And in 6b, the acceleration of the Ford is 2.06 meters per second squared. Now let's look at how to rearrange the equation. For most equations, we can use an equation triangle. However, in this particular equation triangle, the acceleration and the time go on the bottom, and v minus u must take up its own space at the top. This means if we're after the acceleration, we can see that v minus u divided by t will calculate the acceleration. If we're after the time, then we can see that v minus u divided by a will give us the time. But if we cover up v minus u, then it tells us that v minus u is equal to at. Now we can rearrange this equation in two ways. We can rearrange it to find v, in which case v equals at plus u, or we can rearrange it to find u, in which case u equals v minus at. So that gives us four ways that we can arrange this equation. Let's look at an example. A ball is dropped from a window at 0 meters per second and accelerates at 9.8 meters per second squared towards the ground. It hits the ground 3 seconds later. What speed does the ball hit the ground? Well, in this question, we are trying to calculate v, the final velocity of the ball. And we know from our equation that v must be equal to at plus u. We're told in the question that the acceleration of the ball a is 9.8 meters per second squared. The initial speed of the ball u is 0 meters per second, and the time the ball was falling was 3 seconds. We can substitute these numbers into the equation. We now know that v is equal to 9.8 times 3 plus 0, which is equal to 29.4 meters per second. So this must be the velocity of the ball as it hits the ground. In this example, a squirrel is sitting on a bin. It sees a dog and runs away. If the squirrel starts running from stationary, that's 0 meters per second, and accelerates at 1.5 meters per second squared, how long does it take the squirrel to reach its top speed of 9 meters per second? So in this question, we're looking for a time. And the time is equal to v minus u over a. we're told that the acceleration of the squirrel is 1.5 meters per second squared, and that the initial speed of the squirrel is 0, stationary, and that it reaches a top speed, final speed, of 9 meters per second. We can substitute these values into the equation. Now we know that t is equal to 9 minus 0 divided by 1.5. And this is equal to 6. So the time must have taken 6 seconds. Pause the video and attempt task 2. Let's check the answers for task 2. Question 1. The time that the car is accelerating is 5 seconds. In question 2, the time that the P is falling for is 5.1 seconds. In question 3, the maximum velocity of the sprinter is 10 meters per second. In question 4, the speed of the paperboy is 9 meters per second. In question 5, the initial speed of the car is 6 meters per second. And in question 6, the initial speed of the dog was 2 meters per second. Now let's look at how we can use acceleration as a negative number to calculate deceleration. A deceleration is a negative acceleration. It tells us that an object, person, or vehicle is slowing down. For example, a motorbike is travelling at 30 meters per second before its driver applies the brake. Over the next 10 seconds, the bike decelerates to a speed of 5 meters per second. Calculate the acceleration of the bike. We can use the same equation. Acceleration is v minus u over t. However, this time, our initial speed of 30 meters per second is larger than our final speed of 5 meters per second. When we substitute these numbers into the equation, we can see that v minus u now equals 5 minus 30. This will of course give us a negative number. So we can now see that a, the acceleration, is equal to minus 25 divided by 10. Minus 25 divided by 10 is equal to minus 2.5. So minus 2.5 meters per second squared is the acceleration. Or we could say that the deceleration was 2.5 meters per second squared. In this example, a runaway train is travelling at 60 meters per second. Friction is causing it to decelerate at a rate of 2 meters per second squared. How long will it take the train to come to a stop? So in this question, we're looking for a time. And we know that time is equal to v minus u divided by a. And we know that the train is decelerating at 2 meters per second squared. So we can put the acceleration as a negative value of minus 2 meters per second squared. We'll keep the initial velocity at 60 meters per second and the final velocity as 0. So we now know that the time is equal to 0 minus 60 divided by minus 2. This gives us minus 60 divided by minus 2. And this is equal to 30 seconds. Pause the video now and attempt task 3. Let's check our answers. In number 1, the car decelerates from 20 meters per second to 10 meters per second in 2 seconds. What's the acceleration of the car? It's 10 minus 20 divided by 2, which is minus 10 divided by 2, giving us minus 5 meters per second squared. In question 2, we have a horse approaching a jump at 15 meters per second. It pulls out of the jump and its speed reduces to 0 meters per second. This happens over a 2-second period. What's the acceleration of the horse? V minus u this time is 0 minus 15 divided by the time of 2, so we end up with minus 15 divided by 2, which is equal to minus 7.5 meters per second squared. In question 3, we have a bowling ball leaving a person's hand at 3 meters per second, striking the pin 2 seconds later at a speed of 2 meters per second. Calculate the acceleration of the bowling ball. So we have 2 minus 3 divided by 2, which is minus 1 divided by 2, which is equal to minus 0.5 meters per second squared. And in question 4, we have a car travelling at 4 meters per second, and it decelerates 1 meter per second squared for the next 10 seconds. What's the final speed of the car? Well, we need to use v equals at plus u, which is minus 1, because we're going to use a negative acceleration for the car, minus 1 times 10 plus 4. And this equals minus 36 meters per second. So this car in question 4 ends up travelling in the opposite direction.